Alright guys, welcome to vodcast 4.3. We're going to talk a little bit about nuclear reactions. Sorry that it's not super exciting. I suddenly realized as I was setting up to record this one that I didn't have all the massive videos and bells and whistles that I've had in a few videos. So we'll see if in the next couple of chapters we can't amp that up a notch. But for tonight, pretty much plain text. Sorry about that, guys. So nuclear reactions, we've been talking about atomic structure, and of course the nucleus is the center part of the atom. Okay, that's where the protons and the electrons are. So in chemistry, most reactions happen on the electrons on the outside, but there are some things that occur within the nucleus, and those are what we call nuclear reactions. And so, of course, our main focus there is going to be that of radiation. Okay, but to get to understand this, real quickly, we're going to briefly go over the parts of a chemical equation, because part of doing nuclear reactions is knowing what a reaction overall is. So we're going to talk a little bit about what the parts of a chemical equation are, and you'll see that this will come back in a future unit as well. So everything on the left-hand side of the arrow, okay, so you guys are sort of used to seeing chemical reactions written like this. Remember that the arrow means yields, or it means produces or results in. It's almost like the equal sign in math, except that the way that, at least that we're going to use it here, it's sort of going in one direction. It's going from this side to that side, much like the way we read. So the stuff that you start out with, the stuff over here on the left-hand side, that's called the reactants. Everything on the right-hand side are called products, and in this case we've only got one, but in many cases we've got a lot more than that. The big numbers, okay, in front of chemicals are called coefficients. And then the little tiny numbers that we've been talking about and using for molar mass and stuff like that, those are called subscripts. So just sort of keep that in mind as we roll throughout the rest of this, because you can't really understand how to do nuclear reactions if you don't understand what a reaction looks like. Now that we've seen that, our central idea behind really any chemical reaction, but even when we're talking about nuclear reactions, is that of the law of conservation of mass, which says that matter cannot be created or destroyed in an ordinary chemical reaction. Now, technically speaking, a nuclear reaction is not really an ordinary chemical reaction. We can sort of have some destruction of matter here, but we're not really going to get into that this year. If you take AP Chem or you take physics, you might get a little bit more into that kind of stuff. We're going to treat it as though you can't destroy or create matter, and what that means for us is this: that grams of reactants equals grams of products. And really, more to the point, it means that if I had a mass number on the reactant side, that I have to get the same total mass number on the product side. Okay, so basically reactants equals products is what I'm looking for here. Okay, so just keep that in mind when we start to do the reactions here in a minute. And this is an example, sort of a pictorial representation of a nuclear reaction, and this is also an example of what we call radioactivity. Radioactivity is basically where a nucleus of an atom, in this case radium, okay, is unstable. Now, there are all kinds of reasons for the instability, but one of the biggest is you start to get a lot more neutrons than you have protons. That tends to make the element overall unstable, the nucleus. And so to make itself more stable, it essentially starts to spit out parts of itself. Okay, and so this radium atom spits out this piece here that we're going to call an alpha particle. Remember, that's what Rutherford was shooting at the gold foil. Okay, it was this right here. And it has a mass of 4, an atomic number of 2, which makes it the same thing as a helium nucleus. And when that happens, radium changes into a different element. This is something that's pretty important. In fact, it's one of those deals that the alchemists were trying to do for thousands of years. They were trying to turn lead into gold. The process of that is called transmutation, where something changes from one element to another. And that's what happens in a lot of radiation, is that radium here turns into radon, which is a different element, different atomic number, okay? And that's what the end result of this radium emitting the alpha particle, it turns into radon. Now, if you look at this, okay, and here's what I really want you to see here. The atomic number on the left-hand side, okay, this is the left-hand side of the arrow, okay, so the reactants, the atomic number is an 88. If we go over to the right-hand side, what we have is an 86 plus a 2. And if we add those up, we have to get 88. And that's what the law of conservation of mass says, that we have to have the same numbers on the product side that we have on the reactant side. Okay? And that applies not just to the atomic number, but it applies to the top number as well. And if you remember from our last lesson, the top number is the mass number. So 226 on the left-hand side. And then on the right-hand side, we get 222 plus 4. And if we add 4 to 222, we get 226. And so everything equals out the way it should. Okay, that's what you're always going to be looking for. We're going to do a couple of reactions here. And it seems like it's really complicated, but it's really just a matter of making sure that everything on the left adds up to everything on the right. Okay, so real briefly, what are the main types of radiation that we're worried about? There are 3 types that we're going to talk about in this class. There are actually more than that, but the 3 are sort of the classical 3 that we always hear about, and these are the ones that we're going to be concerned with. The first one is called alpha decay, and that is what Rutherford used. He was basically, the particles that he was using were emitting what we call alpha particles. An alpha particle is a helium nucleus. It is this 4/2 helium. And it's really common if you've got really big atoms. The symbol for alpha is right here. It's the Greek letter alpha, okay, basically a lowercase a in the Greek alphabet. And sometimes what we can actually do is we can substitute that out for the helium. Now we would still have to write the 4 and the 2, okay, but if I took the helium out, I could sub that in there and put alpha particle instead. So sometimes you may see that instead. Really, technically, either way would be fine to write it if you put the helium or the alpha, but you need to know both ways just in case you see them in different ways. Maybe on the EOC or something like that, they might have the alpha in there instead. It doesn't really matter because what really matters to us are the numbers on the bottom. And again, if you check these out, I've got a 92 over here on the left-hand side. I've got a 2 plus a 90, which gives me 92 on the right-hand side. And then if we add up the mass numbers, 238. Okay, and then on the right-hand side, we've got 4 plus 234, which is going to give us 238. So everything has to add up. Always the case. Everything always has to add up. So our second type of radiation is called beta decay. Basically, what happens in beta decay is that an electron is emitted. Now, here's what's weird. Electrons aren't in the nucleus, right? What's in the nucleus are protons and neutrons. But the strange thing is that neutrons are basically made up of smaller particles, and the smaller particles that they're made up of are essentially a proton and an electron canceling each other out to make it neutral, to make it a neutron. It's really a little bit more complicated than that, but that's close enough for what we need. And so what happens is the nucleus spits off an electron, and it's really not, there's no electron in the nucleus. The electron is part of a neutron, so the neutron splits itself apart and it spits off the electron part, and so what that does is it leaves an extra proton in the nucleus. Now what that does as far as our equation is that, remember, electrons have a negative charge, okay, so they basically count as a -1 for atomic number. So that means that if we have 90 over here, this is a thorium atom, and if we've got a 90 over here on the left-hand side, and we get a -1 over here, that actually changes the atomic number. So basically, again, it's a transmutation, just like alpha decay is, but instead of going down by 2, in this case, it goes up by 1. Okay, so 91 plus a -1 still gives us 90. Electrons essentially don't have any mass. I mean, of course, they do have mass, but it's so minimal that it doesn't really matter. And so 234 plus 0 gives us 234. Okay, so this guy over here, the electron, that is the beta particle. And again, just like we talked about with the alpha particle, you could really sub in that beta particle there and put that in the place of it. So just be prepared in case you happen to see that. And our last form of radiation are what we call gamma rays. Now, the good thing about gamma rays is that they're energy. And if you look at what a gamma ray is, that's the symbol for gamma right there. Okay. Gamma rays don't have any charge or mass. They're pretty much just pure energy. In fact, they're part of the electromagnetic spectrum that we'll talk about in a couple of chapters. They're essentially the same thing as like light and microwaves and radio waves, just at a different frequency and wavelength. So when they're given off, they don't really affect the whole reaction that much, except that if you notice, you see this guy here? Hopefully that looks familiar to you because that is an alpha particle, okay? So often what happens is that like this uranium nucleus like we had before, it spits off an alpha particle, and so we've got the 2 plus 90, that gives us 92, 4 plus 234 gives us 238. But at the same time, it has to get rid of some of that energy. And this happens when a nucleus is what we call thermodynamically unstable. You guys really don't have to know what that means, but basically it means it has too much energy, and so it's going to try to get rid of some of that extra energy, and that's when it emits gamma rays. Now, if we briefly sort of run back through these, alpha particles are pretty big, okay? 4, 2, okay, they got a mass of 4. So they're really big and slow. They can do a lot of damage, but they're easy to stop, like a thin piece of foil will stop alpha particles. Electrons or beta particles are much smaller. They have an essential mass of 0, and so they're moving pretty quick. They can penetrate it through stuff a lot deeper. You're going to need a much thicker piece of metal or something like that to be able to stop a beta particle. And then gamma rays, since they're basically energy, they're moving at the speed of light, which is essentially as fast as something can move without doing in some really weird hyperphysics. So that means they have a lot of energy. They move really quick, and that means they can penetrate a long ways. It would take like a foot or so of concrete to be able to stop a gamma ray from penetrating something. So these tend to be a little bit more dangerous in the fact that even though they don't have much of a mass, they're moving really quickly, really high energy. Okay, so what does all this mean for us? What do we have to do with this information aside from like memorizing definitions and knowing what they are? Essentially, this is what you're going to see on the EOC. You'll see a couple of these, probably not a ton, but one or two, where you are given a nuclear equation and you have to balance it. So first off, how do you know that this is different from the normal balancing that we'll do later in the year? Everything will be in nuclear notation. In regular balancing, we don't have like number on top of number here in nuclear notation. And so all you have to do is you got to figure out, usually there'll be something missing on the product side, so there'll be a question mark or a blank there, okay? And so you got to figure out what goes in that blank. And it's really not that hard. Remember that the goal is that you have to have everything on the right-hand side, okay, over here, equal everything on the left-hand side. So I've got a 19 here and a 20 here, so I need this side here to add up to be 19. So if I already have 20, the only way I can get to 19 is if I throw in a negative 1. Okay? Now I've already got a 40 here and a 40 there, so I really don't need anything here, so that's a 0. And again, what has the negative 1 charge and a mass of 0? Well, that's our good friend the electron, or conversely, you could call it a beta particle. Okay, either way would be fine. So that's beta decay. Okay, relatively simple. And let's work another one real quick. Again, you got a blank here. We've got 88 on the left-hand side. We get 86 on this side, so that means that we need 2. Okay. Over here on this side, we got 226. We got 224 over here, which means that we need 4. Okay. And if we need 4, well, essentially, what does that equate to? Well, 4 basically means that it is an alpha particle. Okay, so we could write it as 4,2 helium. Or we could, sub in the alpha particle. Either way really is perfectly fine. It sort of depends on what way they have it on the test. So remember, the gist of this is just that you're trying to add everything up. Okay? So relatively simple. We'll work through probably 10 or so of these on a worksheet just to make sure that you get this. And make sure that you know what the types of radiation are, what the symbols are. And usually they want to know like how fast they move that we talked about a little bit earlier. And I'll try to pop that stuff in so that you guys can see that actually on the notes. Okay? Sorry again for the lack of like massive excitement and pictures and all that stuff in the videos, guys. I'll try to definitely do a little bit better on the next couple. I was trying to rush these through so that I could get test graded. Okay, so thanks a lot, guys, and we'll see you on the next video.